go now to examples. Okay, and the collection of this symplectic, of the submanifolds is called the symplectic foliation. So I think Camille will talk more about foliations with leaves of varying ranks in his lectures. Okay, but it's an example of a singular foliation. So let me just draw some pictures of what the symplectic leaves may look like in examples. So as we saw in R2, any bivector field is necessarily of this form and is Poisson by dimension reasons. So, you know, if you choose whatever different functions, for example, this one, you know, you see that symplectic leaves will look as follows. So now this has, you know, a zero-dimensional leaf here at the origin where this function vanishes, and at any other place this is not degenerate. So you have an open symplectic leaf, which is the complement of the origin. Just to give you a sense of things that, you know, can happen. Of course, you could take f of xy to be x. Then in this case, the y-axis will be a collection of zero-dimensional leaves, right? So you have zero-dimensional leaves everywhere here. Every point here is a zero-dimensional leaf. And you have two other symplectic leaves on this side and on this side. Is that clear enough? Good. So let's draw some more pictures. I think the next example is in the problem set. So remember that I talked about groups acting symplectomorphically on a symplectic manifold, and nice action free and proper, and how the quotient was Poisson. So you may wonder about how to describe the symplectic leaves of this guy. Okay, so you can do that, but you know, a particularly nice situation in which you can describe the leaves is when this action is Hamiltonian. Which means that you have, assuming that you know a little bit of symplectic geometry, that you have a moment map. If you don't know about that, just skip this example. Okay? And when you have a moment map, you can perform what is called symplectic reduction, Mars-Weinstein reduction. And there's a natural way in which Mars-Weinstein quotients, they sit inside this quotient here. And these are the symplectic leaves of that. Okay? The connected components, more precisely, are the leaves. So I think I asked you to show that in the problem set. Okay, so action here, free and proper. Okay, so subclass of that is okay. The class of duals of Lie algebra. So we saw that given in Lie algebra, its dual has a natural Poisson structure. So what are the symplectic leaves of that? These are the so-called coadjoint orbits. This matches one possible way that you can endow coadjoint orbits with symplectic structures via symplectic reduction. Right, so the coadjoint orbits are the symplectic leaves. So let's just draw some pictures, work out some examples. Okay, So in the case of SO3, like the dual of SO3, so I wrote here, so these are all three-dimensional. These are all like three-dimensional Lie algebras, like R3, and these are the bivector fields that you get, right? They just encode the bracket relations, right? So on SO3, the bracket of x, y is z, y, z is x, and z, y. Oh, it's wrong. Yeah, and z, x is y. Oh, x, z is y. Yeah. Anyway, so there are typos there. Sorry about that. I did warn you. So yeah, I'll get to that. Yeah. So in the case of SO3, so you can actually realize that so SO3. So in this case, you can check that this guy is a Casimir. So this function has 0 Hamiltonian vector field, which on the other hand means that it's constant on the symplectic leaves, right? And in this case, you can actually show, and this I think is in the problem set, that the level sets of this function will be exactly the symplectic leaves. So this, well, you always have 0, and away from 0, right? You have like concentric spheres. So these are the symplectic leaves. And the symplectic forms are just like multiples of the area form in this case. Okay. And then in the case of SL2 star, then you have a Casimir. So this is a function that is constant along the symplectic leaves there. So it's an evolution with any other function with respect to the bracket. And you can actually check that the level sets are, yeah, so this is like three-dimensional, right? So here are the level sets. So again, in this linear Poisson structures, the origin is always a singular, is always like a symplectic leaf by itself. So you have like this. And like this. Sorry about the drawing. I'm making an effort here. So that's how the symplectic leaves look like in this case. These are the coadjoint orbits of SL2. And yeah, so the other case, this SB2, so the Berkeley algebra. So it's defined by x, y, being 0, y, z being y, and z, x being minus x. Right? And in this case, the symplectic leaves, they look like this. So the z-axis contains, you have a z-axis worth of 0-dimensional leaves. And then you have 2-dimensional leaves, which are planes like this, that look like the pages of a book. Okay, with this straight line of 0-dimensional leaves as the binding. Okay, that's how it looks like. Anything else I want to say about those things?
As a matrix algebra, this would be triangular matrices.
That's right. That's right. Yeah. Yeah, exactly. Mm-hmm. And then, as I said, you have this class of Poisson Lie groups and homogeneous spaces. So Yeah, I mean, I'll spare you formulas. I'll just try to tell you qualitatively what happens in this example. So, as I said, you have SU2 as a compact semi-simple regroup inherits this non-trivial Poisson structure. In this case, is something, given by an R matrix, whatever, something relatively simple to describe. You can find actually the formula for the bracket and everything. And S1 sits in there as a diagonal matrices in here. And you have a quotient to CP1, which is S2, which is the Hopf vibration, right? So what I'm telling you is that, like this carries a non-trivial Poisson structure and this carries a non-trivial Poisson structure, okay? And the Poisson structure here is actually pretty similar to this. So basically we have two types of symplectic leaves. So you have zero-dimensional leaves, which are parametrized by a circle. And then you have another circle worth of two-dimensional leaves, just like here, right? You have circle parameterized in two-dimensional leaves. So you can write the explicit formulas for that, okay? And you have a circle. Anyway, like you have a circle parameterized in two-dimensional leaves. And the symplectic foliation here in this example is actually pretty simple. So it vanishes at the North Pole and is symplectic everywhere else and vanishes here quadratically. Okay, and this map is something that takes this circle worth of zero-dimensional leaves to this point, and each two-dimensional disk here, which is a symplectic leaf, to this disk over here in a symplectic way. Okay, just to give you an idea of what can happen in these examples. Anything else I want to say about this? Yeah, so perhaps I should just mention, without really explaining much.
What breaks symmetry? It's a homogeneous space, right? So what is the reason that there's a certain point which is distinguished and there's a certain circle which is distinguished in the Hopf vibration?
I mean, what can I say about that? I mean, like, I'm telling you like a Poisson structure. I mean, why should it be? I'm just giving a Poisson structure here. Yeah, it's homogeneous in the sense, yeah. So a good point is that homogeneous doesn't mean, that's a good point. So homogeneous doesn't mean that the action preserves the Poisson bracket. It means something else. It means that this is a Poisson map. Here you have a Poisson structure as well. And here you have a Poisson, and here you have a Poisson. If this guy is zero, this means that you're acting by Poisson diffeomorphisms. And then what you're saying should happen. But because you have this guy, this is not an action by Poisson diffeomorphisms. I think that it's a good point, actually. Yeah. Good. Yeah, so maybe I should also mention that in these examples of Poisson Lie groups, they actually show up in pairs. The Poisson Lie group always has a companion, which is the dual group that shows up in the story. And in this case, the dual group of this guy is actually the Lie group that integrates this Lie algebra here. Like this book group. Okay, right, and this example of log symplectic perhaps is ever here. I should say something about that then. Yeah, that's why I have to make sure to say something about that. So in the log symplectic example, so remember that there was a distinguished one codimension one submanifold that captured the singular locus of the Poisson structure. So you have two types of symplectic leaves. So one exercise, it's actually in the problem set, is to prove using Weinstein's splitting theorem that around points in this distinguished submanifold, the bivector field looks like this. So it has the symplectic factor plus something that looks like this. So you'll be asked to prove this. There are a few things that you can deduce from this. So first of all, you can see that there are two types, okay, in general. So you have two types of symplectic leaves. So the connected components of the complement of this guy, right? And symplectic leaves which are inside this codimension one submanifold, right? So you have Z, and you have complement, which are symplectic, and inside this guy you have symplectic leaves which are codimension 2, right? So we lost 2 dimensions here, so these leaves have the codimension 2. So this Z is actually a Poisson submanifold of codimension 1 with symplectic leaves of codimension 1 inside this thing which has codimension 1. So it has codimension 2 with respect to the initial Poisson manifold. Okay, so that's how they look like. Good. So, okay, so one thing is, okay, what else is there locally? So I told you, so we have the splitting theorem, and in the splitting theorem, there was a symplectic factor and a totally degenerate factor, right? So we saw that the symplectic factor has an intrinsic meaning on the manifold, so you can patch them together into submanifolds, which we call leaves, symplectic leaves, right? So you have, so here you have S, N, right? So this is the symplectic part that locally has coordinates QI, PI, and you have here this guy with coordinates Y, right? And this guy vanishes at the point here. Okay, so again, as we saw, the symplectic factors, they can be assembled intrinsically into symplectic leaves, into submanifolds, right? So what to say about this other factor, right? It has an intrinsic meaning as well, but just up to isomorphism. Okay, so what you can check is that take another point on the same symplectic leaf, and if you put one of this, Weinstein splitting neighborhoods over here, the symplectic factor will be an open of the leaf here. So we may have, we call this Z, Z prime, N prime. Okay. N prime. So what one can check is that there is a neighborhood of N around the point Z, and there is a neighborhood of Z prime, of N prime around Z prime, and a Poisson isomorphism between this and this. Okay, except that, if you move away, this guy can shrink. So you can really talk about a well-defined germ if you want, but, but that's what happens. And there's actually something more intrinsic that happens, which have to do with, this co-symplectic, this Poisson transversals, whatever, but let me just formulate it like this. Okay? So this is well defined up to Poisson isomorphism. And in the problem set, I outline a way, like a method that you can use to prove this. Okay, so basically, you can, by moving along Hamiltonian vector field, local flows of Hamiltonian vector fields, you can bring this transversal over here to the same point and reduce the problem of, comparing neighborhoods of two guys, around the same point. And what one can show is that around this point, these two Poisson structures, here and here, they are what's called, gauge equivalent. They differ by a two form, as I explained in the problem set. And this two form is exact. And you can use a Moser type argument to, make them coincide. Okay, so this is in the problem set. Anyway, there's something else, not unrelated, but let me just explain something else that you find locally. Which is a natural Lie algebra structure on the conormal spaces to a symplectic leaf. So if you have a point X, take a leaf, symplectic leaf through this point, right? You can consider the normal space at that point, and you can consider the conormal, which is just the annihilator this tangent here, which by the skew symmetry of the bracket coincides with the kernel of this pie chart map. Okay, so I'm fixing a point, I look at the kernel of, so this pie chart goes from T star to T, right? I look at the kernel, it's a subspace of T star at X, and what I'm claiming is that this subspace has a Lie algebra structure. Okay, so how do you define it? So here is how you do it, one way to do it. Okay, so you take two covectors at the point X, you realize them as differentials of functions, and you can choose these functions so to vanish using the splitting theorem if you want on S, and you just take their Poisson bracket and their differential, and this gives a well-defined Lie bracket there. Okay, so so you have this, transverse Poisson structure that is well defined up to isomorphism, and at each point there is a Lie algebra associated with it. Okay, so the moral here that you should take home is that, Poisson geometry kind of mixes, symplectic geometry on the leaves, foliations, because, you have a foliation of symplectic leaves, and Lie theory, not only because you have natural examples from Lie theory, but because you find at each point a Lie algebra in a natural way. Okay, so the Poisson manifold has all that. Okay, so let me just explain very briefly the relationship between these two objects, like the Lie algebra on the conormal spaces and this transverse Poisson structure. And the relation is very simple, is that, so the dual of this Lie algebra on the conormal space is a linear Poisson structure, where on the on the normal space here, right? So if you think about a local splitting, where this guy has coordinates qi and py, and this has the coordinates y, what you would be saying is that you have a Lie algebra structure, right? And this in there. Right. And the relationship is that, the dual of the Lie algebra, sorry, you have like a linear Poisson structure in here, and that this linear Poisson structure here is the first order approximation to this Poisson structure over here, right? Remember, this Poisson structure vanishes here, right? So we can just take its first order approximation. This will be a linear Poisson structure, which is exactly dual to this Lie algebra that I was describing before. Okay. So that's the relationship. So this takes me to a very classical question that is worth mentioning, just because it has really motivated a lot of research in this field of Poisson geometry, which is the linearization problem posed by Weinstein in this classical paper of 1983, that asks, when a Poisson structure that vanishes at a point is locally isomorphic to its linear approximation. When can you find coordinates that actually take, a possibly nonlinear Poisson structure into this linear part? And, there is a very vast literature on this. I cannot, justice to everyone who worked on it. So let me just mention some very, just some facts. So the first big theorem in this story is, basically saying that, well, this Lie algebra, by the way, is called the isotropy Lie algebra at a point, that if this Lie algebra is semi-simple and compact, then you have linearization. Linearization is possible for any Poisson structure whose, first order approximation dually is like this, right? And this was a very hard analysis proof using like Nash-Moser and things like this. And there is a more geometric proof by Meinrenken and Fernandez that, on the other hand, use symplectic groupoids or in ideas of integrability, to basically do the averagings that will guarantee that certain cohomologies vanish. And there is a very recent paper, maybe from last month or something, by Johan Marcoux and Fernandez, that generalize all this to certain submanifolds of Poisson manifolds, like including symplectic leaves, and this is like very general, and you can find lots of references there, probably. Okay. Right. So the last thing I want to mention. So any questions so far? Okay, so just like then a brief summary. So picture to have in mind, locally a Poisson structure on a manifold is a product of two things. You have a symplectic factor and you have another factor that degenerates at this point, right? This symplectic factor has an intrinsic meaning on the whole manifold as symplectic leaves. So you have a decomposition of your Poisson manifold into submanifolds, and each one of them is symplectic, and more, you can recover the full Poisson structure from the information of the leaves and their symplectic structures. Exactly, because you can take Poisson brackets by restricting them to the leaves. Poisson brackets of functions by restricting the function to the leaves, right? And then there is also something very interesting going on in this transversal direction. So namely, you have, for each leaf, you have a well-defined, transverse Poisson structure, but up to isomorphism, right? And, the first order approximation to that is a linear Poisson structure that gives you, a Lie algebra on the conormal space to each point, right? And if you take, of course, 2 points, the Lie algebras are isomorphic. Okay, so you have this mixture of, symplectic leaves and Lie algebras in this direction. Good. So let me mention just like, some invariants that one can define on Poisson manifolds. So one of the basic invariants, so this goes back to this paper by Lishnerovich in the 70s, is the following. So we have this observation. So basically I mentioned that on multi-vector fields, so it's sort of the only place I'll need this scalping bracket, but I mentioned in the previous lecture that on multi-vector fields, you have a bracket that is a kind of graded bracket that extends the usual commutator bracket of vector fields, and it has the property that it takes something of degree k and something of degree L and gives you something of degree k plus L minus 1. Okay. Now, if you're given a bivector field, which is an element in X2, then you can define an operator that is the scalping bracket with this fixed bivector, right? And this will have the effect of, just raising the degree of a multivector field by 1, right? So then you get something like that. And a simple observation is actually the fact that, let me just write this here, that when this bivector field is integrable, this is in fact equivalent to this operator squaring to 0. So it's a differential. So you can talk about the cohomology of this complex, right? And this is called Poisson cohomology. And as is usual for cohomologies, like the first, the lower degree cohomologies have nice geometric interpretations. So this can be all like exercises. The zeroth cohomology gives you the Casimirs of the Poisson manifold. Again, this functions that Poisson commutes with any other function, or equivalently the functions whose Hamiltonian vector fields vanish. And then in degree 1, what you have is the difference between Poisson vector fields, meaning vector fields that preserve the Poisson structure. So this is also defined in the problem set properly. And remember that Hamiltonian vector fields, they all have this property. So they are subsets of Poisson vector fields, a subspace, right? And this H1 pi is this difference. And H2, which turns out to be relevant for many of this linearization and normal form theorems, is what encodes infinitesimal deformations of a Poisson structure modulo trivial deformations. So it's a kind of tangent space to the modular space of deformations of the Poisson structure. Right? It can make sense of H3 as well as obstructions to, extending a Poisson structure to a formal one, whatever. And remarks is that they tend to be very hard to compute. So for example, if you set your Poisson structure to be 0, then the differential is 0. And you see that this Poisson cohomology is given by just the multivector fields, which shows that they can be infinite dimensional, even for very simple spaces, right? Another remark is that in the symplectic case, because in the symplectic case, we have an isomorphism between T and T star given by the symplectic form, you can actually show that this Poisson cohomology becomes the Dirac cohomology. Okay, so in the symplectic case, it's just the Dirac cohomology. But in general, it can be very interesting and not easy to calculate, even in simple examples. If you take the plane R2, then the Poisson cohomology will really depend, and you take a function that vanishes at the origin, The Poisson cohomology will depend on the type of singularity. It will have information about the singularity of the function at that point and things like that. And even on dual of the algebras, there are recent calculations again by Johan Markut and what's this? Seitzer, the student, right? So they calculated even like some classical, simple three-dimensional examples. The Poisson cohomology was not known until recently. Yes? The what? Yes. Well, yeah. Right. That's right. That in the symplectic case is an isomorphism. Yeah, that's exactly the point. Yeah. So let me just mention to wrap things up, one important class that one can define on any Poisson manifold that also may show up in talks, which is called the modular class, which at least, let me assume that the manifold is orientable, is basically the measures, the existence of volume forms which are invariant by Hamiltonian vector fields. Okay, so what am I saying? Yeah, so what am I saying here? You know that, for example, in a symplectic manifold, you always have this alluvial volume form, right? So if you have a symplectic manifold, and take this volume form, which will be preserved by any Hamiltonian vector field just because the symplectic form is preserved by any Hamiltonian vector field. On the Poisson manifold, the situation is much more interesting, right? So you may not have volume forms which are preserved by all Hamiltonian vector fields. Yeah, right. Good. So yeah, so how do you define this modular class? So that's so here's a definition. So if you fix now on a Poisson manifold, if you fix a volume form, so suppose it's orientable, then given any function, you can consider its Hamiltonian vector field and see if this volume form is preserved by it or not. Okay. But what happens is that this is again a top form, and therefore will be a multiple of this volume form. Right. So this gives you again a function. Right. So what I'm saying is that I have an operation that takes a function to another function. You can check that this operation is actually a derivation of functions, and therefore gives rise to a vector field. And that's the modular vector field associated with this volume form. Right? I defined it using, a volume form, fixing a volume form first. So this gives me a Poisson vector field. Now, what one can show, it's also a result by Weinstein, is that if you change the volume form, you change this guy by something Hamiltonian. So it doesn't change its class in Poisson cohomology because that's what H1 is. So it's modular Hamiltonian vector field. Okay. So this class is well defined. And it's, in many cases, it's non-zero. So for example, for log symplectic, it's non-zero. And I think there is also a problem in the problem set. Just like, there are very simple examples in R2 where you can check this, right? So it's in the problem set as well. Yeah. So that's what I wanted to say today. Thanks.
Yeah, so questions?
Yeah, so what do you put when most persons you and what
I'm sorry.
When will the root perspective?
Yeah. Oh, almost is just that I don't require the Jacobi identity. Yeah. Okay. So, well, I mean, you may have something, right? So in these non-holonomic systems, first of all, what happens? So the whole point of a non-holonomic system is that you are constrained by a distribution that is not integrable. That's why it's non-holonomic, right? And therefore, there is a way that you can realize, well, this distribution or something related to it as the image of a bivector field. So there's no chance this bivector field will be integrable because, the whole thing is non-integrable. But you can still use the formula. We still use the bracket, whatever, to have a geometric formulation of the equations of motion and things like that. And there are situations that you can improve the integrability of the bracket. For example, if you have symmetries, right? I mean, if you take a quotient of this bracket that had no properties at all, and you take it to another place where perhaps Jacobi is still not satisfied, but the characteristic distribution will be integrable. Right, so what I'm trying to say that there are two levels of integrability. Okay, that's a good point. So you may have a bivector field, right? And you can consider this. And in principle, what you have here, right, is just like this distribution, nothing else. And at each point, you have a non-degenerate, so that's linear algebra. So at each point, you have a non-degenerate form on this image, right? And then you have a second thing, which is this R is integrable. Just this R is integrable. Okay, so you have leaves tangent to this. And then what you can show is that this form actually will give you an almost symplectic structure on each leaf. Right? And then you have the third level of integrability, which is, and that's actually an exercise in the problem set, is showing that in this situation, pi is actually Poisson, if and only if, these leafwise forms are closed. Okay, so that's a third, there's another level of integrability. So sometimes you also have things which are in between here. For example, things which are called twisted Poisson. You have a free form that controls the lack of integrability. So there are things in this direction as well.
Other questions?
Good point. Where is the problem set? So, yeah, where is it? Well, I sent it to Cedric.
It will be online on the official webpage this afternoon.
Yeah.
Maybe I have a quick question. Probably it's on the problem set is the relation between the modular class and the modular character for the algebras.
Yeah, it's not right. Yeah, it's not in the problem set, but it could be in the problem set. Yeah, that there's a in the case that's a good point. In the case that the Poisson manifold is the dual of the algebra, this modular class is related to the modular theory of the algebras. So for example, the dual of the Lie algebra will have vanishing modular class if and only if the Lie algebra is unimodular, meaning that the trace of the adjoints are zero. Yeah. So there's a theory of there's a modular theory for Lie algebras that matches this theory for Poisson manifolds in the case of linear Poisson structures. Yeah, this could have been a problem set. Yeah.
Okay, I would say let's thank Enrique again.